Hello and welcome back to Stats Coach. Today's video is all about understanding Excel's ANOVA output. So here on the left we have some data from 3 different farms, and these farms each produce potatoes. In this case, each of the farms is producing 100 potatoes. So each of the potatoes is weighed, and their weight looks like it's somewhere between maybe 0.7 pounds and 2.5 pounds or so. So we're testing to see if each of the farms is producing the same size in terms of weight of potatoes. So Excel and the ANOVA analysis will tell us if one of them is different. So the way that we actually conduct an ANOVA analysis is we go to Data and Data Analysis. Now, if you don't have data analysis in Mac, you have to go to Tools and Excel add-ins. In Windows, I believe you have to go to File and Options and then Excel add-ins. But there are other videos on YouTube to explain those, and they're pretty straightforward. But anyways, I already have it downloaded or added. So I go to Data, Data Analysis, and then we go up to ANOVA Single Factor, which is the very top one, and click OK. Then you would highlight everything. So you can go across and then down. We do have labels in the first rows. Typically, alpha is going to be 0.05 because that's a 95% confidence level. But if it is, let's say, 99% confidence level, you could do 0.01. And then you can specify your output range. I already did that, though, so I'm going to do it in a new worksheet just so I can delete it later, since I already did it previously. But this is the ANOVA output that you'll get, which, again, I've done up here, so we'll look at this for now. So this is the ANOVA output that Excel is giving you. And then down here, I've put popular abbreviations for all of these statistics, as well as how they are actually calculated. So let's go through each of these. The top part is pretty straightforward. It's just the count in terms of the number of values in each column, as well as their sum, their average, and their variance. Down here is where it gets a little bit more interesting. So this value here is the sum of squares due to treatment, which is often abbreviated as SSTR. So this is calculated by this. It's the sum of the squared difference between column means and sample mean times the number of samples in the column. So in layman's terms, what that means is sum of squares between is a calculation of the variation between farm 1, farm 2, farm 3. Okay, and that will make a little bit more sense when we discuss sum of squares within. So sum of squares within, or sum of squares due to error, is often abbreviated as SSE. It is calculated by doing the sum of squared differences between each value and the value's column mean. So sum of squares due to error, or sum of squares within, is all about how much variation is there within column 1, within column 2, and within column 3. So that the variation is only compared to within each column, whereas between column 1 is compared to column 2 is compared to column 3. That's kind of a short explanation for between versus within. The total sum of squares is just sum of squares due to treatment plus sum of squares due to error. So these two added together. And we can see that up here. 79 is 20 plus 59. Now, degrees of freedom between are the number of groups minus 1. So here there are 3 groups, farm 1, farm 2, farm 3. So minus 1 gives us 2. Right? And then the degrees of freedom within is the total number of observations, sometimes called n sub t. And then you subtract the number of groups. So here there's 300 observations because you have 100 in farm 1, 100 in farm 2, and 100 in farm 3. And you subtract out the number of groups, which is 3. So n sub t minus k, or number of observations minus number of groups, is 297. And again, just like the sum of squares total, the degrees of freedom total is just these two added together. So degrees of freedom between plus degrees of freedom within. Now, for the mean squared due to treatment and the mean squared due to error, it's abbreviated MSTR and MSE. These are just this row or this cell divided by that cell, and this cell divided by this cell. So We can see that down here. This is just SSTR divided by degrees of freedom between, and this is just SSE divided by degrees of freedom within. Will give us your mean squared due to treatment and mean squared due to error. These values are basically just taking the squared variances due to treatment and error and putting them in terms of the degrees of freedom, which is basically in terms of the size of both your the number of groups that you have, as well as the number of observations within the groups. Okay, and then the F statistic is where you can really start to test your hypothesis, and that is just the MSTR, so mean squared due to treatment, divided by mean squared due to error, and we see that calculation here. Okay. Now the F statistic we compare to an F critical value, which Excel is automatically calculating for us based on the alpha that we specified. If for some reason you had to calculate this manually, you would do equals f.inv, plug in your 0.95 or whatever other confidence level you want to test, degrees of freedom between and degrees of freedom within. That's how we're getting this F critical value. For the p-value, that is calculated using a right tail F distribution. So you would plug in equals, again, if you had to do it manually, it's automatically calculated in Excel, but if for some reason you were doing it manually, it would be equals f.dist.rt for right tail, and then you plug in the F statistic calculated here, your degrees of freedom between, degrees of freedom within, and true, because that's going to be cumulative. But again, here, if you're unsure about what all of this means, you could check out an earlier video where I explained how to actually evaluate an F statistic and evaluate your null hypothesis using the F statistic and the p-value. But based on the F statistic, since it's larger than our F critical value, that's one way we know we can reject the null hypothesis. The other way we know is the p-value is really, really small. It has 18 leading zeros, and then so 0.00, 18 zeros, and then 1, 3. So because it's smaller than your alpha of 0.05, we can also reject. Rejecting an ANOVA analysis means that we know that one of them is significantly different than the others. If we had to take a guess, we could look at the averages for each of the column, and it looks like farms 1 and farm 3 are producing similar sized potatoes, and probably farm 2 is the one that is different. So that is a short explanation of everything in Excel's ANOVA output. If you have any further questions, don't hesitate to comment down below, and I appreciate you watching the video. Thanks.